So now, folks, we want to solve a problem using the method of Lagrange multipliers. I'll review these steps in just a second, but let's look back at what we did in the last video. So if we were to clean this up slightly, and you don't need to do this, the basic idea is we're going to come up with a system of equations that we want to solve. And we can always use this constraint equals 0 equation, and we'll talk about that in just a moment. But then the other system of equations, the other equations that we're going to get to form this system, is by asking the question, where are the gradient vectors of this constraint curve, which in this case all the gradient vectors are orthogonal to it. And we're asking the question, where are the gradient vectors of that constraint curve parallel to the gradient vectors of our function, our surface that we're working on. So for example, at this point right here, the gradient vector on the surface is pointing about this direction, and on the surface here it's pointing about this direction. On the surface here it's pointing about this direction. And it's right here that we see we have the gradient vector on the blue constraint curve is parallel to, and I should be careful here, folks, these don't have to be the same length, so let me just kind of extend this one out a little bit further, that the gradient vector on the blue constraint curve is parallel to the gradient vector on our green surface level curve lines. So that's precisely the location we're going to find, and we're going to find this location right here. To do that, we're going to solve the equations. We want the gradient vectors of f to be parallel to the gradient vectors of g, and for parallel we need a scalar multiple. Normally you would expect to put something like a, but we said in the last video we'll put lambda. So given that information here, we can see that this is our procedure for finding the using the method of Lagrange multipliers to find the absolute maximum and minimum on a closed constraint curve. In this case, we're going to solve this system of equations right here. We want to solve this equation and this equation simultaneously. And we'll look at how to actually extrapolate the equations out of this in just a moment. Then what we're going to do is, once we solve this, we're going to find values for x and y. We'll also find values for lambda, but they won't be useful in evaluating the function. So we'll take the x and y ordered pairs that we get and plug them back into the original function f to figure out where our absolute maximum and absolute minimum is. As a reminder, folks, this method only works assuming that the gradient of our constraint curve is not 0, or the 0 vector. So let's go ahead and take a look at how this works now. So in this problem, and we'll look at an image of this in a second, but in this problem we want to use the method of Lagrange multipliers to find the absolute maximum and minimum of this surface right here. So here we've got this surface, and let's see here, that surface would be what? Well, it would be a hyperbolic paraboloid. We want to find the absolute maximum, absolute minimum on this surface, given that we're constrained by this equation right here. We've got to obey this equation. So let's see how we can come up with this system of, in this case, nonlinear equations that we want to solve. So our goal is to solve the system, and the first one is that the gradient of f needs to equal the gradient of some scalar multiple of the gradient of g. That's the first equation. Well, that tells us we need to come up with some constraint function, g of xy. So here we're going to let g of xy be the equation x squared plus 2y squared minus 4. That means that the original constraint is equivalent to saying g of xy must equal 0. If you were to set this expression equal to 0, you could recover the original constraint equation that we were given. Okay. But the issue now is that we've written this as a function of the two independent variables x and y, and so then it makes sense to talk about the gradient of that function, assuming that it's differentiable and that the gradient is not 0. Okay. So, in fact, that gives us the second part of our system of equations. Let's call that 1, and let's call this 2. And for 2, we need to solve the equation g of xy equals 0, meaning we want parallel gradient vectors at a place where we meet our constraint. So how do we come up with an actual system that we can work on solving? Well, we compute the gradient vector. So if we compute the gradient vector of f, the gradient vector of f would be So this is our this will be our grad f right here. And in this case, the gradient vector of f would be minus 8x for the first position and 2y for the second position. Remember, just as a reminder, because it's been a little while, the gradient of f is equal to partial f partial x, comma partial f partial y. And I'm just constructing that vector here. And we're going to set that equal to lambda times the gradient of this function g. The gradient of the function g will be 2x, 2x and then for the first coordinate, and 4y for the second coordinate. So this was our gradient of the constraint function g. Okay. So now we can construct a system of equations, because if these two vectors are going to be equal to each other, then their coordinates must be equal. So our first equation is that minus 8x must equal lambda times 2x. And we'll call that equation, let's call it equation 1a, because we started with this original statement that the gradient vectors need to be parallel. We called that 1. And so that's our first equation. Our second equation then would be that 2y must equal lambda times 4y. That's equation 1b. And then our third equation is the constraint must equal 0, which our constraint was x squared plus 2y squared minus 4 equals 0, and that's our equation 2. So we've got these three equations now, and we've got three unknowns, and that's sort of the beauty of using this method of Lagrange multipliers, is that by introducing the scalar lambda, we now have a system of three equations, three unknowns, which we may be able to solve. Folks, as far as the steps for this go, you will do these first couple steps every single time. You'll set the gradient of the two functions equal to one another with a scalar multiple well, we're going to set them to be scalar multiples of one another, so we've got that scalar multiple lambda. And we can set that constraint function equal to 0. And from there, we can build a system of equations. So you'll always be able to do this. What's challenging about these problems, folks, is that this is usually a system of nonlinear system of equations, and those can be very difficult to solve. So I will show you a couple of tricks in this problem, and then I'll show you a couple of tricks in class. But in general, there is no algorithmic way to solve a system of nonlinear equations. So let's go ahead and tackle this. The first thing is let's look at equation 1a there. And what I can do is I can rewrite that as, so we've got minus 8x is equal to 2 lambda x. And if I take all the terms over to one side, we get 0 is equal to 2 lambda x plus 8x. And then in this case, it's relatively straightforward to write this expression here in factored form. That will not always be the case. In this case, though, we can factor out a 2x from each of those terms, leaving us with lambda plus 4. So this gives us two solutions here, this first equation, either that x is equal to 0 or lambda is equal to negative 4. So let's just put those bits of information in our back pocket for just a moment. Then if we look at equation 1b, similarly we can rewrite this. So we get 2y is equal to 4 lambda y. And if I take all the terms over to one side, this is what we end up with. And we can factor a 2y out of that, leaving us with 2 lambda minus 1. This gives us two solutions as well. Either y is equal to 0 or lambda is equal to 1/2. Okay. Now, given these bits of information, we may be able to now go through and solve our system entirely. I want to point out that in this case, and this is not always true, in this case, if I were to plug, so let me just say it like this. Note, if you were to plug lambda equals negative 4 into equation 1b, so we learned from equation 1a that lambda would, if lambda is negative 4, that would satisfy the first equation. If you're to plug that information into 1b, you wouldn't get any new information. You would still find that y is equal to 0. Or if you were to plug lambda equals 1/2 into equation 1a, so in 1b we learned that 1b is satisfied when lambda is equal to 1/2. If you were to plug that into 1a, in this case you get no information, no new information. But in some cases you may. So it might be that if you took lambda equals 1/2 and you plug it into this equation here, maybe you find that x equals 7 satisfies that. Or maybe when you take lambda equals -4 and you plug it into this equation here, maybe you find some information that will be handy to continue solving this system. But in this case, it didn't help us. Okay? But if we were to plug, let's say, x equals 0 into equation 2, which was our constraint equation here, what we get is 0 squared plus 2y squared minus 4 needs to equal 0. And if I solve this for y, I get y is equal to plus or minus the square root of 2. And if we were to plug y equals 0 into equation 2, then that would give us x squared plus 2 times 0 squared minus 4 needs to equal 0, which gives us x is equal to plus or minus 2. And so now we have some ordered pairs that we want to go test. The ordered pairs that we want to test are these ordered pairs right here. We've got the ordered pair when x was 0, we could have the square root of 2 for y, or when x is 0, we could have minus the square root of 2 for y. When y was 0, we found that x could be 2 or -2. And these are, in this case, 4 ordered pairs, and you're not necessarily always going to have 4. You might have 2, you might have potentially even none. But these are the values that I'm going to go evaluate in our function, the original f of x, y. So if we do f of 0 comma the square root of 2, we could evaluate that, and we'll evaluate each one of these points in my original function, because these are the candidates through this method of the Lagrange multipliers for me to potentially have my absolute maximums and absolute minimums. In a lot of these problems, folks, these values will be your absolute max and absolute mins. They don't necessarily have to be that. They could be sort of something kind of analogous to inflection points, so you do have to test these. So anyway, we'll go ahead and evaluate each one of these points in the function, and I'll do that now. And so if I were to plug the ordered pair 0 comma square root of 2 into our original function, let's go see where that was again. Screen's frozen. There we go. If we were to go plug it into this original function here, our f of x, y, our surface, remember these are our candidates for absolute maximum minimums, and if we were to plug these points in, then we end up with, we would end up with f of 0 square root of 2 comes out to be the z value 2. F of 0 minus the square root of 2 would come out to be the z value 2. And if we were to plug in x is equal to 2 and y is equal to 0 into this equation, that would give us minus 16 when x is 2, or minus 16 when x is -2. So, from this information, we can infer that that f has, let's go ahead and write this on the next page. We should have room for that down there. Yes, so f has a global, let's say it like this, f when restricted to the constraint, and our constraint was that x squared needs to be equal to 4 minus 2y squared. F when restricted to this constraint has a global max at, and then those were 0 comma the square root of 2 and 0 comma minus the square root of 2, with the max value being 2. And it has a global min, let's say it like this, I guess we should say plural, global mins at 2 comma 0 and -2 comma 0, with min values 16. So again, folks, the whole strategy hinged on this notion of saying we want to set the gradients of the two functions, both our surface and our constraint function that we build based on our constraint information. We want to set them to be scalar multiples of each other. That's the method of Lagrange multipliers. So that gives us this statement here for our problem, and we also include our constraint function. So notice we build our constraint by taking whatever our constraint is and constructing a function of two variables out of it, and then setting so that when we set it equal to 0, we can recover the original constraint. So this gives us these two equations here. From there, we're able to construct a system of equations. When you do this, what's interesting is that you will always have a system of equations with as many equations as you have variables. So notice here we have 3 equations and 3 unknowns. The next part, folks, is nothing I can really teach you. It's because we have to now solve a system of nonlinear equations, and there is no set way to do this. In this case, what I chose to do was work with each of the first 2 equations separately because it was possible to easily factor those. That will not always be the case, and in class I will show you a different method that we'll use sometimes when we're trying to solve these systems of nonlinear equations. But there is no guaranteed way to do this. Finally, folks, once we did this, once we solved this system of equations, we found a total of 4, you could call them critical points if you want. We don't call them that because we didn't obtain them through our differentiation like we did in our section 15.7. But we found these 4 points that are potential locations for the absolute maximum and the absolute minimum on the function f when we restrict it to our constraint. So folks, let's go ahead now and take a quick look at what this looks like on a graph. So you should be able to click the hyperlink to CalcPlot 3D, and then you'll want to download this script and then upload it into CalcPlot 3D. So let me do that now. So folks, what I did here is I uploaded this script in CalcPlot 3D. Let's zoom out a little bit. Here we can see that's what's currently highlighted is the surface that we want to find our absolute maximum and absolute minimum on when we're restricted to a certain constraint. Okay. So our constraint is that we have to be on this curve right here. So this is that curve that we get by looking at, by saying that we had our g of xy set equal to 0. So we have to find the absolute maximum and absolute minimum not on the entire surface, but the points that are on the surface when we restrict ourselves to this red curve. Okay? To show you what that red curve looks like when we're looking at it in the domain, it's these values right here. And so this is this blue curve where we're going to compute the gradient vectors of this constraint curve. We've set it equal to 0. We'll compute those gradient vectors, and then we will set them parallel to the gradient vectors of our surface. Okay? And when we did this, we found that we had the absolute maximum when we were at y was equal with the order pair 0 comma square root of 2 and 0 comma minus the square root of 2. And notice that sure enough, let me remove our blue curve again. Sure enough, when we restrict ourselves to that red curve, that's where the surface has its absolute maximum. Likewise, we found our absolute minimums at the ordered pairs. Let me put this in the traditional orientation. At the ordered pairs 2 comma 0 and negative 2 comma 0, we found that the surface had its minimum values at those ordered pairs there. Folks, I hope this helps. When we get to class, we will continue to work a couple more of these problems, but that's the brief overview of our method of Lagrange multipliers.